Okay, so we just saw the field of rational functions in the indeterminate t. Let me also just note here, you can also similarly define rational functions in any number of variables, because you can look at quotients of polynomials in any number of variables. And we'll revisit this in chapter 8. We're going to turn to rational expressions. And the first thing to observe is, well, what's the difference besides this word expression versus function? So we saw an example in chapter 1. We saw this q parentheses pi, which was polynomial in pi over polynomial in pi, where p of t and q of t are in q adjoint t, and q of t is non-zero. And when if you have a non-zero polynomial and you plug in pi, it stays non-zero because pi is transcendental. So we saw that already, and we saw that this was a field, or maybe I just observed it, I don't remember, but this is a field. The proof that it's a field is the exact same, actually, as the proof that rational functions in t is a field. So it's exactly the same proof. Nothing is different. And that proof is exactly the same proof that q is a field. Nothing is different, except for how you represent symbols. However, this kind of looks like, in a way that we're going to make precise, q, rational functions in t over q, right? However, it's not, because these aren't functions. These are numbers. It's p. When you plug in pi into a polynomial in q, you get a polynomial expression in pi. That's just an honest number. It's no longer a function. Okay? Similarly, q adjoint pi is a function, and their quotient is a number, and their quotient is also a number. So it looks like q adjoint t, but q parentheses t, but it's not the same. But it isn't. It isn't, let's say, on the nose. Later we'll see they're isomorphic, but they're not on the nose. In particular, the elements are not functions, are not functions. They're numbers, right? In fact, they're even real numbers, right? So because pi is a real number. So somehow they're different, and we use a different word to describe this set instead. So this is called the field of rational expressions in pi over q, instead of rational functions, because they aren't functions. Okay, so what's a rational expression? It's kind of like a rational function, but you've determined t by plugging something in. All right, so again, we'll revisit these in the, I believe, let's see, in the next chapter. But for now, let's observe something here. This notation on the left of this guy here in yellow, q adjoint pi, is notation that we've introduced in this chapter. And namely, this should be the smallest field that contains q and pi. Well, what should that smallest field have in it? It should have any powers of pi, probably, because you have pi, so you can multiply pi as much as you want. So q adjoint pi should have all powers of pi, right? It should have, therefore, all rationals times the power of pi for all n and n and pn and q. Should have all of those, because those are field operations. You should be able to add them. You should be able to look at combinations of them, which we might call p of pi. And you should have what? Well, you should be able to divide by them. So you should be able to look at quotients of those because it's a field, right? It's the smallest field containing them. And so you're led naturally to this set. It's not too hard to show this set's a field. And then how do you show these sets are equal? Well, one of the containments is easy, and this is the other containment. Okay. All right. And in fact, more is true. If I were to look at something like a different example, Q adjoin root 2, which we've seen already is like A plus B root 2 over A and B, where A and B are in Q, then what? Well, I claim this is the same exact thing as a rational function in root 2 where the denominator is not 0. So P of t and Q of t are in Q adjoin t, where Q adjoin root 2 is not 0. I claim it's the same exact set. So let's see. So if I have a polynomial in t, a and t to the, let me go up, let me actually write in some of these intermediate degrees. So a2t squared, a3t cubed, all the way up to, all the way up to a n t to the n. And what happens when we plug in root 2? Well, we get a0 plus a1 root 2. We get a2 root 2 squared. That's 2a2. We get 2a3 root 2 because we have a root 2 cubed. And then all the way up to an, it's going to be like 2 to the floor of n over 2. And then, well, I can't think on the spot. It's going to be root 2 to the n, which you can write as either a rational or a root 2, right? Okay, so what do we see here? Well, every other term is rational, and every other term, all the remaining terms have a root 2 in them. So what you can do is you can collapse this into some a plus b root 2, where a and b are in Q. You collapse all the rational ones together, and you pull out the root 2 from the others. So in other words, this set, let me call this set S here. So S is the collection of all, when we plug a polynomial into, root 2 into a polynomial, we get some a plus b root 2. And when we plug it into the polynomial in the denominator, we're similarly going to get some c plus d root 2, where a, b, c, d are in Q. But we know how to compute multiplicative inverses of c plus d root 2, right? C plus d root 2 times the conjugate expression is c squared minus 2d squared, which is not 0 if c and d are not 0. And so c plus d root 2 times, let's divide by that c squared minus 2d squared, is 1. And this, therefore, is the multiplicative inverse of c plus d root 2. So in other words, if we were to put this in a bubble, in other words, S is the collection of all, well, I can move this up as a number plus a number root 2 and then multiply them. But if I multiply two guys that look like number plus number root 2, I again get number plus number root 2. And this is exactly the set we had before. It's the same set, okay? And so what's going on kind of in the background here is rational expressions in this case, a single variable or a single number ends up being exactly the field generated over, in this case, Q by that single new number you're throwing in. And that will always be the case. And if you're throwing in more than one number, you don't look at rational expressions in just pi. You're going to have to add in more than one variable, right? And you're going to have to look at rational expressions and polynomials in more than one variable. Right? So this sort of aside on rational expressions is important because these fields are important. And it's actually the same thing that's happening for things like Q adjoin root 2. It's the same exact thing that's happening. But it's sort of more complicated than what's necessary. We don't need to unravel this each time. All right. So rational functions are honest functions, and rational expressions are what you get when you sort of plug in, you determine the indeterminants in the rational functions. You plug in honest numbers.